This lesson is about solving systems of linear equations in two variables. Here's an equation with two variables. Here's another equation with two variables. When we say a system of linear equations, we mean two or more, in this case two equations. And before I give you the solving techniques, I think it would be smart to spend a little bit of time understanding what it means to solve a system of equations and what it is that we're looking for. So before we get to the technique, follow me on this mental journey. Would this top equation, 2x plus y equals 5, be true if x were 2 and y were 1? Well, one thing we can do is substitute in 2 for x and 1 for y and find out. Well, a little arithmetic here will show that it is true, because as we know, 4 plus 1 is 5. Now, when that happens, we say that the ordered pair 2, 1 satisfies the top equation. An ordered pair, by the way, is just two parentheses and a comma with an x first and a y value second. But 2, 1 is not the only ordered pair that satisfies this top equation. It's also the top equation is also true when x is 3 and y is negative 1. Watch this. If I substitute 3 for x and negative 1 for y, the little arithmetic will show that I do have a true statement here. 6 plus negative 1 is 5. So 3, 1 is another ordered pair that satisfies the top equation. Another ordered pair that satisfies the top equation I found would be negative 1, 7. As you can see, by plugging in negative 1 and 7 for x and y. Now I've found 3 ordered pairs that satisfy the top equation, but this is by no means the entire list. In fact, the number of solutions is infinite, but 3 is good enough for now to prove the point I'm trying to make. Let's now consider the bottom equation. That bottom equation is satisfied by 9, 1, 6, 0, 3, negative 1, and many, in fact, infinitely many more ordered pairs. By the way, I'm not suggesting that this is what you would do when solving this system of equations. I'm merely pointing out that each of these ordered pairs, each of these equations has many ordered pairs that satisfy or make it true. Well, what is a system of equations then? Well, it's two or more equations where the goal is to find one ordered pair that satisfies or works for both. And if you look here, we have stumbled across it. 3, negative 1 is an ordered pair that satisfies both of these equations, and therefore that is an answer and turns out to be the only answer to this system of equations. But of course, nobody wants to do guess and check until you accidentally stumble across the correct answer. That's not very efficient. So now let's turn to efficient strategies that will allow us to solve for x and y without having to engage in guess and check and praying for luck. So, turns out there are many methods that you can use to solve a system of equations. One of them is called substitution. One of them is called the addition-elimination method. There's also a graphing method, and about 3 or 4 more that I haven't mentioned here in more advanced courses. The graphing method is not something that I will be covering here. And the addition-elimination method is something that comes up later in this video. So for now, let's focus our attention on the substitution method. The substitution method is one in which we solve either equation for either x or y so we can make a suitable substitution. You'll see what that means as we go through this problem. Now, when I say we can solve either equation for x or y, I mean we could solve the top equation for this x or the top equation for this y, or the bottom equation for this x or the bottom equation for that y. It doesn't really matter. Just pick a letter and solve for it. Since we can pick any letter and solve for it, I hereby choose that letter. So, let's take this equation and solve it for x. Solving it for x requires that I add 3y to both sides, giving me this. Now, when I say I'm solving for x, I don't mean I'm finding out that x is 11 or 15 or negative 2 or any specific number. I'm solving for x in the sense of isolating it and finding out that x equals or is the same as 3y plus 6. We say this equation is solved for x. Now, once you've solved either equation for either variable, you then substitute that result into the other equation. So, here's the other equation, and here's what I'm going to do to substitute. Since we know that x and 3y plus 6 are the same number, I can take this equation and replace x with 3y plus 6, as I've done here. Now, on first glance, it looks like we've made a much messier equation, but notice there's no x in it. And the fact that there's no x in it makes it very easy to solve relative to the original system. So now I'm just going to show some basic algebra. None of this should look terribly new to you if you've gotten this far in mathematics. But notice I now have the value of y. In other words, for the original system to be true, y must be negative 1. And now that I know y is negative 1, what do I do with that? Well, I can substitute negative 1 back into any y on this page. I could put negative 1 here or here. I could put negative 1 here, here, or here. I could put negative 1 here or any other y on this page. But the question isn't really what can I do, as much as what would be the most practical thing to do with that negative 1. If all the y's on this page are now negative 1, which y should I substitute negative 1 into? Well, it turns out if I substitute it here, it will very quickly get me the remaining portion of the answer. Watch this. By substituting negative 1 in there and just doing some very simple arithmetic, I've now solved for x, which was my missing variable up until this point. And now that I know that x is 3 and y is negative 1, that would be the same as saying the ordered pair 3, negative 1 satisfies the system. Therefore, that is the solution to this problem. Now, I'm done with the problem, but I'd like to go back to the original problem to clear up something I said earlier. Earlier, I told you that we could solve either equation for x or y, and I said we could solve for this x or this y, or this x or this y, and I opted to solve for this x. And I made it sound like it didn't matter. Well, it technically doesn't matter, but some choices are worse than others. I want to show you something that's not a great idea, so that you can see how a bad choice can lead to some ugly algebra. Suppose I had randomly chosen to solve for this variable. Totally fine, but it gets messy. If I were to solve for that y, it would get messy because that y has a coefficient in front of it other than the invisible 1. And so when you have a coefficient in front of a variable, it makes it very annoying to solve for that variable. Watch what happens as I try to solve this equation for y. It's totally doable, but maybe not advisable. To solve for y, I would have to subtract x from both sides and then divide by -3. But after that, the algebra gets ugly, and whether you understand all that or not, I think we can all agree that while we can solve either equation for either x or y, it's not advisable to choose a variable that has a non-1 coefficient in front of it. The two variables being pointed to, the red arrow and the green arrow pointing to x and y, those would have been the two best choices to solve for. The red arrow is the one that I actually did, and you saw that earlier. The green arrow would have also been a viable choice because both of these variables pointed to by the arrows have a coefficient of 1 in front of them. In other words, they don't have a visible coefficient at all, and I would recommend in problems like that for substitution that you choose a variable that has no coefficient, meaning it has a 1 coefficient. If no such variable exists, I probably wouldn't even choose to use the substitution method. So now let's get away from the substitution method and examine our second method today, the addition-elimination method. It's a completely different style of solving. And before I do this problem, I think it would be wise to point out some really obvious facts that are going to become relevant later. So putting the problem on hold, here's obvious fact number 1. If we multiply an equation by any number, we create a new equation. To show you what I mean by that, here's an equation. I think we could all agree 6 equals 6. If I were to multiply that equation by any number, say 2, big surprise, I get another equation. Here's another somewhat obvious fact. If we add 2 equations, we get a new equation. Here's 2 equations. We all agree that 5 equals 5 and 3 equals 3. If I were to add these together, I would get, big surprise, a new equation. 8 does in fact equal 8. Now these arithmetic examples seem a little strange and obvious, but they illustrate these 2 basic facts, which are the fundamental basis for using the addition-elimination method, as you're about to see. So now let's get back to the actual problem and use the addition-elimination method. First, though, one more exploration of a failed attempt at solving this problem. According to the basic facts we just discussed, I can multiply any equation by any number. If that's true, I could multiply the top equation by 4, and that would give me this. But according to the second basic fact, I can add any 2 equations together, and adding the result of the first equation with the second would give me yet another equation. Now, what I've done here is I've showed you that we can use these 2 basic facts any way we like, but some ways are more clever than others. Now, while what I've done is totally valid, I would classify it as valid and useless. In other words, I've followed the rules of math. Everything I've done is valid, but of what value is it to me to have the equation 10x plus 9y equals 22? It's just another equation to add to my system. I haven't made any progress. And if you're wondering what I mean by progress, let me show you. Instead of multiplying the top equation by 4, what if I multiplied it by -5? Now that may seem random to you, but you're about to see why that is an excellent choice for a multiplier. Because if I multiply the top equation by -5, and then I add that to the bottom equation, something very helpful happens. I get a 0y term. And that term basically vanishes because while I don't know what y is, I do know what 0 times y is. It's 0. And 0 plus negative 17x is negative 17x. So by choosing to multiply the top equation by negative 5, I created a cancellation or an elimination of a variable when I added my two equations. And that's ultimately what your goal is. Because once you've eliminated a variable, basic algebra will allow you to solve for the other. Now that I know x is 4, I can substitute 4 into any x on this page that I'd like. But again, the question isn't what can I do? The question is what might be the most productive? Well, I don't know what y is yet, and that is my goal. So not knowing y, it seems prudent to plug 4 in for this x. Watch what happens when I do that. Taking that equation, substituting 4 in for x, makes for a very easy equation to find out what y is. And now that I know that x is 4 and y is negative 2, I simply put my answer in an ordered pair, and I've solved the system of equations. Now, if you're still unclear why I chose to multiply the top equation by negative 5, here's the same problem again. Here was my thought process. I chose negative 5 because I looked here and I said to myself, oh, I wish I had a negative 5 there to cancel the positive 5 below. How can I get there to be a negative 5 where the arrow is? I could multiply the equation by negative 5, and that would give me what I needed. So here's a system of equations that is going to prove a little bit difficult to solve. We're going to have to do something creative here. So I want you to watch as I develop a creative idea. I'm going to multiply the top equation by negative 3. I can do that because I'm allowed to multiply by any number I want. I'm going to multiply the bottom equation by 2, which I'm also allowed to do. Now, of course, it seems arbitrary that I just pick numbers to multiply by. And here's where your cleverness comes in. You have to cleverly choose numbers to multiply that will result in a cancellation of a variable. Notice in this case, after my seemingly arbitrary choices of negative 3 and 2, that when I add my equations together, the x terms cancel out. In fact, my reason for choosing those numbers was to make the x's opposite sign terms, which would then cancel out when I added my equations. So you have to be clever, do some trial and error, do different things, until, by your own clever devices, you get a cancellation of a variable. Because as we've seen in previous problems, once you get a variable to cancel, the rest of the algebra falls out naturally and is quite easy relative to the beginning of the problem. So after a little basic algebra here, we find out that y is 5. Taking any of the original problems, that one just seemed like a simple one to choose, and substituting in 5 for y, ultimately, through a little bit more basic algebra, will lead to a solution for x. And as is always the case, my goal is to solve for x and y, expressing my answer as an ordered pair, and I'm done with this problem. Now I want to turn our attention to a problem that looks the same as the kinds we've been doing in this video, but turns out to be quite different in that this system of equations has no solution, and you wouldn't know it by looking at it. Now suppose we were going to solve this system. I would recommend the substitution method that we saw at the beginning of this video. In other words, because this equation says y equals, I can substitute that expression for y into the second equation. Watch and you'll see. Because y is equal to 2x plus 3, meaning that y and 2x plus 3 are the same number, I can replace this y with 2x plus 3 as they're the same. Multiplying by -2 through the parentheses, in other words, using the distributive property, leads me to something interesting. It leads me to an equation where the 4x and the minus 4x cancel out. It almost seems as though there isn't a variable left to solve for. And we're left simply with the statement -6 equals 7. Well, we all know that -6 doesn't equal 7. In mathematics, we call this an absurdity. It's a statement that can never be true. And when solving a system of equations leads to an absurdity, that tells us that the original system of equations had no solution. In other words, this system of equations can't have a solution because if it did, we would be able to prove that -6 equaled 7, which of course it doesn't. So the bottom line is, when you're given a system of equations and you're going about the normal solving techniques, whether it be substitution or elimination or whatever you choose to use, if at any point the variables disappear completely and you're left with an absurdity, which is any statement that's unilaterally false, the indication is that there's no solution to the original problem. And finally, we turn our attention to something almost the complete opposite of no solution. Now, up until this point in the video, we've only seen systems of equations that had a single ordered pair solution, or in the case of the last problem, no solution. But it turns out there are systems of equations, such as this one, that have what we say infinitely many solutions, and we'll see what that means here in a minute. But you wouldn't know it by looking. This looks like any other system of equations problem we've done in this video. So let's go about solving this the ordinary way. I think I'm going to use the elimination method here using these two basic rules we developed earlier. So in order to use the elimination method, I can multiply any equation by any number. I'm going to choose to multiply the bottom one by 3. I think that's a wise choice because if we take the top equation, leave it alone, multiply the bottom equation by 3, that sets me up to where when I add my equations, the x's cancel. But strangely, so do the y's. And so do the constants. And again, I'm finding myself in a place where I have no variable left. There's no x or y in this equation to solve for. But unlike in the previous problem where I had an absurdity, a statement that can't be true, here I have what mathematicians call an identity. That's a statement that's always true. 0 equals 0 is an always true statement. And whenever you are solving a system of equations and the variables vanish, leaving you with an identity, a statement that's always true, that's an indication that there are infinitely many solutions to this system of equations. By the way, an identity doesn't have to be 0 equals 0. It could be 5 equals 5, or 9 equals 9, or -2 equals -2. Any kind of statement like that that's always true. Now, in most mathematics courses, we would stop here and say that the, quote, answer to this problem is the phrase infinitely many solutions, and that would be the end of it. In some mathematics courses, you'll go further and try to find all of those solutions in some mathematical way. And I have videos that will address that for more complicated mathematics courses. But for now, for the purposes of this video, the answer to this problem is that there are infinitely many answers to this problem. It's almost as if the answer to the problem is this phrase. Now, even though I'm done with the problem, I'd like to just spend 1 minute telling you what infinitely many solutions actually means. I went to the trouble to randomly plug in numbers to the original problem, and I found out that 2, 0 is a solution. I found out that 6, 1 is a solution. I found out that 1, -1/4 is a solution. And the purpose of this video is not for you to see that specifically, rather for you to be reminded that there are infinitely many solutions to this problem. And I could go on and get more. I just stopped after randomly finding 3. And again, these seem kind of arbitrary, and most mathematics courses won't have you list any of these. I'm simply pointing out that as far as the original problem goes, I could find a never-ending list of solutions if I wanted to. But by the way, infinitely many solutions doesn't mean any random numbers you make up will work for the original system. For example, 3, 2, -1, 0, and 5, 7 halves are just randomly chosen ordered pairs that are not solutions, and there's an infinite number of ordered pairs that don't work either. So even though we write infinitely many solutions, and we call that the, quote, answer to this problem, it's worth noting that what that really means is there's an infinite number of ordered pairs that do work, and there's also an infinite number of ordered pairs that don't work. And that concludes the lesson.